In this video we're going to look at combinations. A combination of size R from a set of size n is an unordered subset of size R. So what we're talking about here is we're starting with a set of size n, and from that set we're going to choose R elements. And in this case we don't really care what the order is. So these are unordered, or in this case order does not matter. So for combinations, since order doesn't matter, if we had an element AB and the element BA, those would be the same element since we don't care what the order is. So let's look at a quick example. Suppose we want to determine the number of combinations we have from a set. The set is A, B, C, and we're going to choose 2 elements from that set at a time. In this case, order does not matter, so we're doing combinations. So if we pick A and B, of course, like we just said, B and A would also be the same element. So we'll just write down 1, A, B. We can also pick B, C, and we can also pick A, C. And those are the only elements that we would be able to have from a combination of 2 from a set of size 3. So there's only 3 elements there. Now let's look at how might we determine the number of combinations that we have in general. Now we're going to look at a particular example here, and if you've already looked at how many permutations you have, we're going to use that calculation then to determine how many combinations we have, and then we'll come up with a general equation for the number of combinations. So in this case we're going to look at finding the number of combinations of size 3 from this set that has 4 elements in it. Now the combinations, we just pick 3 from those, and we'll have A, B, C. Another one would be A, B, D, A, C, D, and B, C, D. So there's only 4 possibilities of combinations from that set of size 4, picking 3 from that set of size 4. But if we look at each one of these, what would be the possible permutations for each of these? So if we had A, B, C, we know we would of course have A, B, C, but we could also reorder all of these into different permutations, like A, C, B, B, A, C, B, C, A, C, A, B, and finally C, B, A. How many of them are there in that row? Well, it turns out that we have 3 elements, and by using all 3 of those, the number of possibilities is 3 factorial. So we have 3 factorial different permutations we can make from that combination A, B, C. Now if we look at all the other ones, we would have the same number of permutations from each of them. So we've got 6 for this one, 6 for this one, and 6 for this one, or 3 factorial for each of them. Now if we look at this side over here, this would be all the possible permutations we would have for picking 3 from a set of size 4. So that number of permutations would be P 3 from 4, or 4 times 3 times 2. Now the number of combinations we have is a lower number, a smaller number than that, and we would get the number of combinations by dividing by that 3 factorial. So for each one of these rows we've got only 1 combination, so we would divide by 3 factorial. So divide by 3 factorial, which would give us on the top 4 times 3 times 2. I'm leaving off the 1 of course, and then 3 times 2 on the bottom. Those would cancel and give us 4, which is exactly what we were expecting. Over here we had 4 combinations, so we were wanting the result to be 4. Now looking at this equation here for the specific example, P 4, 3 over 3 factorial, notice that the 3 here is the same. 3, they were choosing 3, and we had 3 factorial on the bottom. So in general, we could use this then to come up with a general equation for calculating combinations. Let's look at the next page and see what that is. Now in terms of notation, we have different ways of doing the combination. We have C parentheses n comma r, and you can see these other ways of doing that, very similar to what we had with the permutations if you've looked at that video. So the general equation for a combination C of n comma r would be the permutations p n comma r divided by r factorial. Now if we put the equation in that we had for permutations, remember permutations was n factorial over n minus r factorial. And so if we put that in with the r factorial on bottom, this would be the general equation for the number of combinations we would have. And if you remember, if you've looked at the binomial coefficients, or if you just remember the equation, this is the exact equation for binomial coefficients. And this is the notation over here that we used for binomial coefficients. And so we'll just use the binomial coefficients. So a lot of times most of the times I'll just use this notation instead of the C n comma r, but all of these are interchangeable. So let's look at an example using combinations. So you go to this store and there's 3 puppies in a cage. You decide you got to have 2 of them. So how many different choices do you have of choosing 2 puppies from the 6 that are there? Well, obviously order doesn't matter. If you pick the 2 puppies, it doesn't matter if you picked one before the other. It's really the same choice. So in this case order doesn't matter, and therefore since order doesn't matter, we know that we're dealing with a combination. And since we're dealing with a combination, we'll use our binomial coefficients. We're picking 2 puppies from the 6 that are total. And so our binomial coefficient we have here 2 from 6. We plug in those numbers like we've seen before, and using the equation up above, do some reduction, and we end up with 15. So we have 15 different choices of choosing 2 puppies from the total 6 that are there. Alright, let's look at another example. Suppose we're going to a store, or someone's going to a store, and excuse me, there's 2 boxes there. One has 7 light bulbs in it, and another box has 3 lamps in it. Now the customer that's going to the store wants to get 2 lamps and 2 light bulbs, so he can put a couple lamps in his living room or somewhere. How many choices does he have of picking the 2 lamps and 2 light bulbs? Well, let's look at each one individually. If he picks 2 lamps from the 7 that are there, does it matter what order he chooses them? No, because he's just going to pick the 2 lamps and go home with those 2 lamps. So order doesn't matter, so we're dealing with combinations. And so for the lamps, he's picking 2 from 7. And if you work through the equation, the total number of choices he has for that is 21. Now for the lamps, sorry, that was for the light bulbs. For the lamps, he's going to pick 2 lamps, and he has 3 possibilities that he can choose from. And using the binomial coefficient, the number of choices he has is 3. Now, since he's picking 2 light bulbs and 2 lamps, he's got a product set there. The number of choices he has is a product set, because he's going to choose light bulbs and he's going to choose lamps. And so the total number would be the multiplication of those 2. And so we have the binomial coefficient for choosing 2 from 7 times choosing 2 from 3, and we end up with 63 different choices. Alright, let's look at one more example. Suppose there's a particular math class that has 13 students in it. The professor arbitrarily decides he's going to give out 5 A's, and so he's going to randomly pick the different people in the class, 5 people in the class to give A's to. And we'll also look at, suppose he doesn't do that, but he decides, well, I'm going to give out 3 A's, 3 B's, 3 C's, 3 D's, and then 1 F. Now he's got to pick from the students that are in the class, the 13 students in the class. So let's look at the first one. Suppose he's going to give out 5 A's to 5 people out of those 13 students. Alright, first ask yourself, does order matter? He picks 5 people and he gives them A's. Does it matter what order he picked them in? No, it doesn't really matter, because they all get A's. It doesn't matter what order that he's given them in, because they'll all end up with A's. And so order does not matter, and therefore we're dealing with a combination. So since order doesn't matter, and he's just picking 5 people randomly out of the 13 that are there, we'll use our binomial coefficient, choosing 5 from 13. And if you look it up in a table or work through the calculation, you'll get 1,287. So that's the number of choices he has of picking 5 people out of the 13 and giving them A's. Now for the second question, with the different number of grades, we see that he'll have essentially a product set from that. He'll have 3 A's and 3 B's and 3 C's and 3 D's and 1 F to give out. And since those are all independent, then or not really independent, but if he gives people the 3 A's, those same people won't get B's. And so he has a different number of possibilities he can give for the A's. Now, if we start with the A's, he'll have 3 people to choose out of the 13 people that are in the classroom. So let's suppose he picks those 3 people and gives them A's. Once he does that, when he goes to give out the B's, he no longer has 13 to choose from because he can't pick those same 3 that he picked for the A's. So in this case, he only has 10 left to choose from, and so he'll pick 3 people out of those 10 to give B's, and so on. So when he gets down to the C's, he's only got 7 people left to choose from, and then for the D's, he's only got 4 people left to choose from, and finally, there's only 1 person left that ends up with the F. We multiply all those together because he's going to do those, in that order, and he can't. He can't give the same people A's and B's, and so multiplying those out, let's say choosing 3 from 13 is 286, choosing 3 from 10 is 120, and so on. Finally, the last one, I forgot to write it down, but the last one, 1 from 1 is of course 1. And so if you multiply those out, you get 4,804,800 different ways that he could give out those particular grades. Now you may be asking yourself, what if he decides to give out the F's first and then work his way up to the A's? Would he end up with the same number of choices? Well, let's look at that. First, let's say he gives out the F's. In this case, he'll be able to pick 1 person from the 13 total in the classroom. And that, of course, is 13 number of ways to be able to do that. Now, once he's given out the F, he's only got 12 people to choose from to give out the 3 D's. That number would be 220 different ways. Then, of course, once he's done that, he's only got 9 people to choose from for the C's, 6 to choose from for the B's, and then finally 3 to choose from for the A's if he does them in that order. Those numbers end up being 13, 220, 84, 20, and then of course 1 for the last one. And multiplying those out, we get exactly the same number of choices, which is a little surprising once you first think about it. But then, by the way we've done the problem, it's not so surprising. He ought to end up with exactly the same number of choices, no matter what order he gives those grades out in.